Hi everyone, welcome back to my channel Pharmagist. Myself Dr. Haimavati. In today's video we'll be learning about bioisosterism. So till now I have been making videos on computer aided drug design. So from now onwards I will be making videos on topics related to pharmacy also, so which are useful for people who are studying Bachelor of Pharmacy, so these topics will be useful for them also. So now let's study what is bioisosterism. Now coming to the definition of bioisosterism, it refers to the replacement of one molecular group or atom with another to maintain a similar biological activity. So here in bioisosterism what we do is we replace a functional group or an atom of a molecule with another atom or functional group in order to maintain a similar biological activity. So it is a concept which is widely used in medicinal chemistry in order to design and optimize the properties of drug molecules. So ultimately in pharmacy, what is the ultimate goal? To get a optimized drug molecule which gives high therapeutic effects with minimum side effects. So bioisosterism is helpful in order to improve the activity of the drug molecule, optimize the activity, and as well as to reduce the side effects which are caused by the drug molecules. So in this way, bioisosterism is a very important topic in drug design. So bioisosters are chemical substituents or groups that have similar physical or chemical properties leading to comparable biological activities. So bioisosters are nothing but they are chemical substituents or functional groups which have similar physical or chemical properties and they have comparable. So the activity will be a similar biological activity. Now coming to the classification of bioisosters, you can broadly classify it into two classes. One is classical and another one is non-classical bioisosters. In classical bioisosters, we have again monovalent atoms or groups and then divalent, trivalent and tetravalent atoms and ring equivalents. So there are 1, 2, 3, 4, 5 different classifications. And in non-classical bioisostates, we have cyclic versus non-cyclic and functional groups and retroisosterism. So how this concept of bioisosterism was first introduced? So this concept was first introduced by a scientist named as Langmuir in 1919. So where he was studying some isoelectronic species, so he introduced the concept of isoelectronic or isosteric concept, and thus the concept of isosterism also was introduced. So isostates are those atoms or groups of atoms or molecules or compounds. They can be either organic or inorganic. So they have same arrangement or same number of electrons. So isostates are nothing but the atoms or groups of atoms or molecules or compounds. So they can be either organic or inorganic. So the molecules can be either organic molecule or inorganic molecule which are having a similar arrangement of atoms and same number of electrons. So isostates means we can consider them as molecules which have similar arrangement or same number of electrons. Now coming to the classification of bioisostates. So the first one is monovalent atoms or groups. Here these are the substances which possess atoms or groups with the same number of valence electrons. So the number of valence electrons in these molecules are same. For example, you can replace fluorine with hydrogen or hydrogen with fluorine, vice versa. Similarly, OH with NH. And here fluorine, OH, NH, they can be replaced with CH3 and then CH3 can be replaced for hydrogen. So similarly, so the number of valence electrons in these functional groups or atoms are same. Hence, we can replace one atom with another atom. So, this is known as monovalent atoms or groups. That means a single valence electron. Next, we have divalent atoms. In divalent atoms also, so these functional groups, they can be replaced with each other. So instead of this, we can take any of these functional group and we can replace, so that there will not be any change in the activity of the molecule. And in trivalent atoms and groups also, we can use these functional groups. And in tetravalent atoms and groups, so these functional groups are used. Next, we have ring equivalents. So these are more important and interesting thing to study. So here the benzene ring, it can be replaced with thiophene, and the furan, it can be replaced with thiophene. So here we can see the arrangement is similar, and it occupies similar what we say overall spatial characteristics. So there won't be any change in the biological activity, because they will be having the same size and occupying the same valency. So here this benzene group, it can be replaced with any of these functional groups without causing much change in the activity or the arrangement of the functional groups. So now let us see some examples. So here we can see this ramotodome molecule. Here this furan ring is replaced with this diazine ring. So you are getting nizatidine. From ramotodome you are getting nizatidine. So here this oxygen molecule is oxygen atom is replaced with this nitrogen, and here this CH is replaced with another nitrogen. So the functional act, what happens is the biological activity is improved when compared to the parent molecule. And similarly we have sildenafil and vardenafil. So in sildenafil you can see in this functional moiety, so here there are two nitrogens, and in vardenafil what is there, one nitrogen is removed and you're having carbon here. So the molecule remains same in spatial arrangement and the volume it occupies and everything, but the only change comes is in the activity of the molecule. Next, coming to non-classical bioisosteres. Here these non-classical bioisosteres, they do not obey the steric and electronic definition which is seen in classical isosteres. So in classical isosteres we have seen that there is similar spatial arrangement and same number of valence electrons are present. But here in classical bioisosteres, they do not obey this steric and electronic definition, and they also do not have the same number of atoms as replacement. So they can be more number or less number of atoms which are replaced. And many of these functional moieties, they behave as one entity. They have any of one of the following characteristics, such as electronic properties, physicochemical properties, conformational or spatial arrangements, functional moiety, critical for biological activity. So these non-classical bioisosteres, they do not obey the properties which are obeyed by classical isosteres. Instead, they have any of these characteristics, such as, that means they have gross characteristics like electronic or physicochemical, conformational or spatial arrangement. So based on this, we can replace one functional group with another functional group. So for example, here a chloride group can be replaced by a trifluoromethyl group or by a cyano group. And aromatic rings, where a phenyl ring, it can be replaced by a different aromatic ring such as a thiophene ring or naphthalene ring. So which may improve the efficacy. So for example, here as you can see, isoprotrinol, when you are replacing, so here this OH group is replaced with this functional group and you are getting soterenol. So here it is not obeying any of the steric or electronic properties. So here the functional group is bigger when compared to the hydroxyl group. So that is why it is known as non-classical bioisosteres. And here in diphenhydramine also, from diphenhydramine you are getting D-carbenoxamine. So here a chlorine is added over here and a nitrogen is added in this benzene ring. So diphenhydramine is converted into D-carbenoxamine. So that is why, because it is not uh, satisfying the properties of classical isostere, but the activity remains the same. And then we have cyclic versus non-cyclic structure. So here the estradiol molecule, it can be converted into diethylstilbestrol and still retaining the activity. So here this cyclic structure, benzene this benzene ring has been, here you can see there is a breakage in bond. So here you can see this bond has been broken. So in diethylstilbestrol the cyclic structure has been broken, and here also you can see this cyclic structure has been broken. So estradiol is a cyclic structure, whereas diethylstilbestrol is a non-cyclic structure, but both are bioisosteres of each other. And next we have amodiaquine and amopyroquine. So here also you can see this is having a cyclic structure, whereas here there is no cyclic structure. If the ring has been broken over here in amodiaquine, but the properties, biological properties are similar. Next is retroisosterism. So retroisosterism, it is based on the inversion of a determined functional group present in the lead compound structure, producing an isostere with the same function. So this strategy aims to optimize the pharmacotherapeutic properties of the original lead compound. So here what happens in retroisosterism is the inversion of the functional group takes place. For example, you can see here. So here you can see this carbonyl oxygen, here it is present above. When you are using retroisosterism concept, so the functional group gets inversed. So here, so the carbonyl group which is present above has been reversed. So this is known as retroisomerism. So inversion of the functional group takes place. So here you can see in this molecule, this nitrogen has been inversed, or this sulfur has been inversed from above position to below position. So here you can see both the atoms have been inversed in their positions. So this is known as retroisosterism. Next, another concept is bioisosteric replacement. So in bioisosteric replacement, it involves the substitution of one chemical group or atom with another that has similar size, shape and physicochemical properties, while maintaining or improving the biological activity of a molecule. So till now we have seen the concept of what are isosteres, what is bioisosterism, and what is the classification of bioisosteres. So now the actual definition is, what is bioisosteric replacement. So when bioisosteric replacement means when you are substituting one chemical group or atom with another chemical group or atom. That means a functional group or atom which is having similar size, shape and physicochemical properties. So these functional groups, they have similar size, shape and physicochemical properties. And what they do, they help in maintaining or improving the biological activity of the molecule. So we are bringing about this change in functional group in order to improve the biological activity of the molecule. So therefore the primary goal of bioisosterism replacement is to optimize the pharmacological and pharmacokinetic properties of a drug candidate. So the ultimate aim of bioisosteric replacement is to optimize the pharmacological and pharmacokinetic properties of a drug molecule. So the different parameters which are to be considered in bioisosteric replacements are size, shape. So in shape we have hybridization of the molecule, bond angles, bond length. So hybridization, bond angles and bond length, they influence the shape of the molecule. And then we have electronic arrangement. So in electronic arrangement, the effects are inductive effect, mesomeric effect, polarizability, charge and dipole. So based on the electronic arrangement of a molecule, this inductive effect, mesomeric effect, polarizability, charge and dipole also play a very important role in the activity of the molecule. And next we have nature of atoms, and then lipophilicity, hydrophilicity, pKa, inter or intramolecular hydrogen bonding, and chemical reactivity, that is the biotransformation, etc. So these are the different parameters which are considered whenever we want to do bioisosteric replacements. So all these factors, they play a very important role in the activity of the molecule, and hence they are to be carefully observed whenever we are considering bioisosteric replacement. So this is about bioisosterism. I hope the concept was clear and informative, and if you like the video, do not forget to like, share and subscribe, and we will see you in the